Hello everyone, this is Ruping from Luceda, and I'm presenting today the design and validation of photonic IP macros based on foundry PDKs, thanks to the contribution from all the Luceda team. So why we come with this topic is because of some realities that we are seeing in this evolution of integrated photonics technology. So first of all, unlike the ways electronics engineer designing for application-specific integrated circuit or the ASICs, where they use a library of standard cells to construct larger systems, there is no such concept as standard cell in integrated photonics. It is just too hard to standardize. There are too many applications where photonics can be used, like telecom and datacom, sensing, artificial intelligence, quantum computing, and so on. And then there are too many ways to innovate at device level to construct a system. And also, there are too many innovations happen at physics level to construct a device. So what we see now is that most of the design houses are developing their own PDK library device and IPs, even if they do work with a foundry that already provide a set of PDK devices. And this is a common situation whether it's a design house who started early and already has a huge repositories of design and IPs, or a newcomer who just started to build up their knowledge. They all have the same concern. There's very little standard procedure in developing and preserving the design IPs, or the existing procedure is largely manual. This can of course cause huge loss to the organization, especially in the current very active domain of integrated photonics chip design, where we see frequent mobility of talents. So whether it's a university or a product development company, they often find themselves not being able to reuse or reproduce what the team members or the former colleagues have done, and it's simply a loss of knowledge, however great work it was. So in this context, we will answer to this issue that almost all integrated photonics innovators are facing today. We will propose the design framework that enables a highly organized and automated PDK library device and IPs development. So first, it's required to organize the data in such a way that all the device or IP information is stored in one place and is easily accessible to everyone within or across the teams. And then the design should be reproduced and reused without any human intervention, thanks to the full automation of the design flow. And lastly, the end users who have habit of all kinds of design tools should be able to use the distributed PDK. And this means for foundry, it should help the foundry to support maximum number of design houses without a design flow change. Or for an end user design house, the PDK should be compatible with their diversified design environment. As an outline, I will introduce our PDK-oriented device and IP development and deployment strategy with the framework of our IPKIS design flowchart. So first, I will go over the component design and validation flow, together with the demonstration of software link with third-party physical simulator tools. And then, just to differentiate with the component design, we call those ones that are made of compact model are as a circuit or sub-circuit, which are simulated using a compact model simulator like IPKIS Café engine. So we will demonstrate a small circuit design of Mach-Zehnder interferometer lattice, the MZI lattice, to show the scalability and flexibility to reuse building block components within the IPKIS PDK framework. And also on the PDK deployment aspect, we will briefly mention the IPKIS link with the system simulators, and also with the EDA tools, which is actually built upon the open access standards. First of all, the IPKIS way of organizing data structure and automation starts with how a building block component is organized. In IPKIS, all the information of various aspects of the component design, including the layout, the physical simulation settings, the netlist, and compact models, are all stored in one place. So if we make an analog of your design as a cake, then IPKIS provides you with this recipe which logs all the ingredients and the cooking information. So following this recipe, you will end up with exactly the same cake every time. So this is what you want when you have a large team, or you have or are going to build up some legacy where knowledge needs to be preserved. So in IPKIS, we define a component. It has its layout information. It has its physical simulation recipe. It has a compact model and also the procedure how this compact model is extracted. So for the component level simulation, most probably the designers have their own preferred tools. Within the IPKIS framework, it's easy to bring in a third-party simulator, and the component design flow is still fully automated. So for example, we drive from the IPKIS PDK library device where we have its physical information, including the layout, technology stacks, and its simulation recipe. And then IPKIS communicate these to a physical simulator like RAME, or numerical FDTD, or CST Studio Suite. And then the simulation result, for example, in the form of a S matrix, is communicated back to IPKIS, and it's processed into a compact model for this device. So this full device design and simulation flow is automated, which means there's no back and forth driving the software from one to another manually or define the device information in two places. The automation ensures the data integrity, and the layout, technology information, simulation settings, compact model is all stored within the IPKIS PDK, even with a third-party simulator involved. Whenever someone else wants to reproduce this design, he can reproduce it exactly the same one, like baking a cake according to a recipe. So up till now, we've shown the characteristics of the IPKIS component creation. To create a component that actually works on a real technology requires much more than that. So here is a V-model chat show how we develop library device components. On the left arm of this V is the design phase of the component, going from specification definition to design, where the layout can already be verified by the design rules, and finally to creation of the design of experiment and design tests. So now we go up to the right arm of this V, which is the validation phase. We carry out the test of the chip, then extract a model which will be used to validate against our initial assumptions made at the first design phase. And finally, with the PCM and trend chart information, we can incorporate the process variation into the model and validate it against the component performance specs we've given from the beginning. So now in the validation phase, there are some important aspects that our team has learned through years of integrated photonics technology platform development, and we've made it available through our IPKIS product. So we've provided initial approximate device model and can be incorporated into the PDK infrastructure so that it's easier to integrate experimental and incremental improvements. Also, as the simulation model is tightly coupled to the layout, it saves a lot of time to create test site design or create circuit design. The advantage of pre-simulate test designs based on initial models also lies in the fact that it can help to avoid many essential errors. And it also assists to bootstrap model extraction process. It ensures that the device parameters can be extracted and saves time later. So concretely, to extract waveguide model, for example, we can make use of an Mach-Zehnder interferometer circuit. We design it in IPKIS and we use the model and simulate it with the IPKIS Cafe. We can use this model and fit it with the measurement results. The fitting can be custom done within the IPKIS, which is powered by Python. We can use Python packages, including the popular ones like SciPy or NumPy and so on, for mathematical calculations and array data processing. So to summarize this model extraction process with a flowchart, which comes from the test data import and normalization. Then we can perform a first manual bootstrap to fit the measurement results with the initial model we provide from the IPKIS Cafe engine. And this saves some time as we move on to the automated fitting and automated validation of the fitting. And finally, these can be established into a fully automated extraction routine. And here we show an example of a parametric analytical model extraction for a directional coupler with varying coupling length, which is actually used as a building block of the MZI lattice filter circuit design that we will later briefly mention. So using the extraction process we've just described, we extract a length-varying analytical model from the measurement results of a series of directional coupler devices with different length values, as noted by different colors here on the transmission spectrum. So specifically, here we use the optimize function from Python SciPy package. It takes a target function and the measured data as input. It adjusts the parameters of the function until there's a good fit. The measured data consists of multiple measurements for various coupling lengths, and SciPy will be able to take the full data array for fitting optimization. And then we end up with an extracted model, including the extracted directional couplers, coupling coefficients kappa and lumped kappa 0. Now that we've developed our building blocks, the waveguide and direction couplers on a specific foundry technology, we can put them together into a circuit design. We can create it in a fully parametric and hierarchical way in IPKIS. So here is a schematic representation of a cascaded MZI lattice design, basically working as a filter device. So it's constructed with several unbalanced MZI devices and with different designs of directional couplers and delay lines at each cascade, which is used to achieve a certain FIR filter window. So after we've constructed the circuit, since each of the subcomponents has parametric layout and parametric circuit model, and they're fully hierarchical, we can get the circuit layout and its simulation model right away. And then we can inject some process variation impact into our waveguide model. For example, the phase noise. We can get performance statistics results of the circuit design. For example, here the crosstalk histogram. So based on this proposed PDK component design, validation, and deployment procedure, we've developed a system design example which demonstrates the power of this framework. So this is the same lattice filter design I've mentioned earlier. Since we have the parametric analytical models of the directional coupler and waveguide, and also thanks to the fact that the layout and model is tightly coupled within IPKIS, we can synthesize this circuit simply by specifying high-level system specifications like the center wavelength, the FSR, and power coupling ratio values, so which is obtained from a reference paper here, and for which we call this method the specification-driven design method. So to further illustrate the design scalability enabled by the IPKIS framework, we reuse this MZR lattice filter component, place and route 3 stages of the MZR instances like a tree, and give different FSR values to the component, and it will give an 8-way multiplexing or demultiplexing response. So the above are all realized within the IPKIS tools within the same PDK framework. Of course, if you'd like to bring in your own software tools, for example, the BPI Photonics for circuit or system simulation, then there's also automated software link between IPKIS. So this creates the IPKIS circuit layout designed from the schematic entry in BPI. And lastly, also on the design and IP deployment aspect, we want to make sure that the distributed PDK package and content can be accepted by the most of the audience, whatever design flow and tools they are using. In the meantime, also we want to ensure the content they've created using a third-party tool is also remains in the IPKIS design framework or the IPKIS PDK framework. So the standard that we support on the EDA interoperability is open access, and we demonstrate it here with our software link with Mentor's Tenor tools. On the screenshot is the same MZI lattice P-cell we've just created. You can now instantiate a Photonics P-cell within the Tenor L-edit, for example. So we have also demonstrated with Mentor the entire schematic-driven design flow from schematic capture, schematic-driven IPKIS cafe simulation, and schematic-driven layout and assisted waveguide routings. And once again, these are built upon the open access standard and can be deployed within any open access supported design tools. So that is an overview of PDK-oriented design and IP creation strategy I'd like to share today. And as a summary, we've discussed first the PDK component design and validation strategy, where we've automated the device CAD flow from component layout to physical simulation and model extraction. We want to stress that all the design data and design information remains integral in the same framework and can be reproduced and reused, which is the key to the IP management within and across the teams. Also important is that you can bring in your own design tools, for example, Lumerical FDTD and CST tools, and the simulation knowledge from these third-party software also remains part of the PDK. And we've also shown the automated model extraction flow. We've demonstrated the procedure for parametric analytical model extraction and the possibility to incorporate process variation impact into the model. Also, this extraction procedure is also fully automated and is stored as part of the PDK. Then regarding the circuit design or the PDK deployment, we've shown a design case of a lattice filter. It uses the parametric building blocks of which the layout and model is tightly coupled. This enables a specification-driven design method where the layout and simulation model are synthesized by software automation. Lastly, we want to stress that our PDK-based design and IP can be deployed in various design flow and environment. We have automated software links with third-party tools like VPI. Our IPKIS users have also developed links with other simulation tools. Now, our EDA interoperability is powered by open access standard, and we've shown our software link with Mentor's tenant tools. So there are some aspects in this chart that I wasn't able to cover today, but you are very welcome to contact the Luceda team for more details. And thanks a lot for your attention, and we will look forward to hear from you.